9.2. This is actually a pretty short one. Maybe you could even do this as a demonstration so long as you had students helping collect your temperatures. So what I've got here, and I'm gonna be moving quickly, I just got my water at the right temperature. And you got a cup of, so this one is ice, this one is water. I made sure that my water is at 0 degrees Celsius. It was sitting in ice water. So same temperature, but I have liquid and ice. And it's the same amount of mass. I use the scale, it's 100 grams of each. I'm gonna be measuring out 100 grams of hot water. This is sitting at 50 degrees. It doesn't have to be, but you're just gonna make sure that it's the same, it's measured when you do the experiment. Because the last investigation was 50 degrees, I went ahead and stuck with that. But you'll need 2 cups measured out at 100 grams. Or whatever mass you went with the other ones. So try to be as close as possible because we're looking for consistency. The main point of this investigation is we have ice and we have water. They're both at the same weight, both at the same temperature. How's it going to impact the temperature of the actual experiment? And so we're going to get our thermometer. I'm going to go ahead and put it in the cold water first because that temperature is going to be easier to read. The ice is going to have to melt. So go ahead and mix in our hot water into our ice and cold water. This one's going to melt, so I'll give it a little bit of a stir, and I'm going to stir this one. You could have your students hypothesize which is going to be at which temperature. Will they be the same? Will they be different? You make sure that you give them some good stirring. I would hypothesize that because the ice actually has to go through a phase change, which means you need more energy, this is going to be a lower temperature. It may even, you can hear it's still ice. Whereas the water, that's going to move up in temperature. So the water, this is perfect. I'm at 25 degrees. So that was a good mixture, half and half. So it got me to in the middle. Whereas my ice water, I don't even have to measure this. As long as it's stirred enough, I can tell you it's still sitting at 0 degrees. We'll leave it in there to let it cool down. Stir it up a bit. So this is why you could either have a couple stations or do this as a demo and students could just fill out. It's not a lot of data. But then this opens up for great discussions about, hey, different states of matter having different energy amounts and what it takes to go from one state to the next. It's not just that this ice was the same temperature. In order to get the ice into liquid, that takes energy, and then to heat the liquid up, that's more energy. So yeah, I'm sitting at just above 0 degrees. I wonder if you can calibrate the thermometers so I could say, hey, this is 0 because it's ice water. But you're close enough to 0 that we can see, hey, that was very different, even though I had the same mass of water and ice, and let students see that. This one got much warmer than the ice. So they're not the exact same, it's going through different processes. If you can get that graph where you get that energy step up, that might help clue students into, hey, you have to go through this entire phase change, adding energy in to go from ice to a liquid. And that's where all that energy went. Okay. Make sure I'm turning everything off. I think these are pretty fun labs. 9.2 coincides with 9.1. Maybe you can do those two together. And this one is really just a front back. So not very long. You can pair those two up together. You've already got all the same equipment, so you might as well go for it. All right, I hope you guys enjoyed that demonstration, and I will catch you guys in the next video. Bye.